How do you do, ladies and gentlemen, and boys and girls? I'm Julius Sumner Miller once again, and physics is my business. And this time, our special business is the thermal expansion of stuff. Notice how I use that word. Thermal expansion of stuff, especially concerned with solids. Solids. Remember, to the best of our knowledge as earthbound creatures, all matter is either solid or liquid or gaseous. I say for earthbound creatures. There is a new kind of stuff now in the laboratory, as the British call it, plasma, electrically charged stuff. And indeed, there may be stuff in a different state elsewhere, which travel to planets elsewhere and stars remote may reveal. But anyway, the thermal expansion of solids. A classical experiment which is not ever really properly explored, as we shall see. The classical ball and ring. Now, what do we do usually? We show that this is a brass ring and this is a brass sphere. They are metals. They expand when heated. We show that the ball cannot pass through the ring, the hole. This suggests very clearly two things. Either the hole is too small or the ball is too big. And because I'm a charitable man, I'll let you think whichever you wish. The hole is too small or the ball is too big. So now what do? We will make this a virtual demonstration and imagine its consequences. We heat the ring in a flame. We heat the ring in a flame of a Bunsen or Mecca burner. And if I do it long enough, I can then pass the ball through. Aha. So somebody says, I understand that. The hole got bigger. The ring got bigger. Of course, these things may be true. Now, as all of you know, I am not so much interested in what we know as I am in what we understand. This is much more important. Accordingly, if we understand what has happened here, the following question can be answered. I have here some metal plates. Here is an aluminum plate with a little hole in it. Here is an aluminum plate with a little hole in it. Here is a plate. Here is a plate. It happens to be rectangular or square. It has a teeny-weensy hole in it. I can see the light. Question. Problem. I heat these plates uniformly. How could I do that? I could put these plates in the oven of my stove at home and heat them. So they are heated everywhere uniformly. Some of the plates are circular, some are rectangular, and they have little teeny-weensy holes. Question. When the plates are heated, what does the hole do? I'll give you some choices. One, the hole does nothing. That's a very good thing to have happen, because I plan in the future to do a lesson on relativity where we will see that Einstein took hold of an experiment whose results were nothing, and he made relativity of it. So nothing is important. So the holes do nothing. The holes get bigger. 3, the holes get smaller. Or I'll let you make that one smaller and that one bigger. I don't care the order. So what do you think the holes will do? Do nothing, get bigger, get smaller. Now, I am led irresistibly to refuse to tell you, because it is more exciting if you engage yourself and your teachers and your classmates and your mothers and fathers and uncles on the question, what does the hole in this plate do? Oh, says some, say some, gets bigger. No, it gets smaller. So I'll tell you the best way to learn the truth of matters. Those of you who think one thing should get together with those who think the other and argue it out. And then, of course, you can do the experiment. One more exciting little dramatic investigation regarding thermal expansion of solids. Here is a ring of metal, a ring, and it has a diameter of its own stuff. Not welded or soldered or brazed, but part of the ring. let us say that this is a very good ring, a very good one, a very good one. And I put this in my oven and heat it. Question, does the ring stay circular or does it warp? Does it stay circular or does it warp? And would you believe it, boys and girls, I have gotten tens of thousands of letters regarding this little inquiry, in most of which the answers were wrong. But anyway, let's consider another. A bimetallic strip. Here is a strip of stuff brazed to another strip of stuff, and they are not the same kinds of stuff. Accordingly, they have different coefficients of expansion. I'm going to heat this bimetallic strip here in a flame, and watch what happens. Watch. Look at that. Look at that. It is bending. Bending. Now, I'm prepared to tell you that one side is brass, and the other side is iron. And I want to know, did it bend on the iron side, toward the iron side, or did it bend toward the brass side? And so you see, I am raising some exciting little inquiries. More on expansion. I have here 2 pieces of glass rod, so it looks, 2 pieces of glass rod. I assert, however, that one of them is glass and the other is quartz, and I'm going to heat them in this flame. And I want to show you a very remarkable thing. I'm heating them both, the glass and the quartz. I'm going to heat them until they get red hot, and remember, color is a thermometric property. And then I'm going to immerse them while red hot in a beaker of ice water. And what would you expect? Would you not expect them to shatter? Let's assume they are heated enough. I see some yellow flame there, which is characteristic of sodium glass. Watch it now. Now let's, I call to your attention the fact that they have both shattered. Whereupon I say as follows. I made a little mistake. I thought one was quartz and the other was glass. So you see what experiment in the laboratory means. Sometimes things go as you wish and sometimes they do not. But what I wanted to show you is this. The glass one would indeed have shattered into 1,000,000 bits. Here, I'm going to show you that. Watch, watch. Oh, look at that. Oh, look, see, 1,000,000 little bits. But the quartz one would not, because quartz has a very low coefficient of expansion. Now, here is another demonstration which you can do for yourself. Here is a metal rod, and here is a little L-shaped wire which marks against a certain scale if we can get tight on it. Now I am going to, oh, no, I thought my flame went out. No, I'm going to heat that. I'm going to heat that, and if we can see the scale right tight, at right angles to it, I hope you can see. I'm sorry, we had a little disaster. I turned on the gas too much. Do you see the adventures which can come when we do experiments in the lab? No hurt, the hose just blew off. This is experiment. Consider another. Here is a long rod, aluminum. Here it rests against a registering meter, and I am going to heat this rod. If we can get a view of this scale here very closely, it reads 0 to begin with. I'm in a little trouble because I don't have my heat source. I detect a slight change in the length of this rod, ever so slight, but nevertheless it exists. So I have an interesting little question for you, a wonderful question. Consider a railroad rail that runs, let us say, from Los Angeles to San Francisco. That's about 400 miles. A steel rail. Supposing that was one rail, and supposing we assume that between the coldest or lowest temperature and the highest change in temperature, we might have 25 degrees change in temperature between the lowest and the hottest in the course, say, of a night. Question, How much do you think that steel rail would expand? 400 miles of it. Now, you know the steel rails are laid so that there is a little gap between successive ones. That little gap is very small indeed. But here is something for you to calculate. The steel rail, one rail, between Los Angeles and San Francisco being 400 miles long, suffering the change in temperature I have suggested, would expand, what do you think, a foot, 10 feet, 50 feet? No, I'm going to tell you, 600 feet. 600 feet. Isn't that fantastic? So those little gaps between the successive rail lengths between here and San Francisco, those little gaps add up to 600 feet. That's absolutely astonishing. More about expansion. A wonderful thing. How many of you have seen popcorn? Everybody in the world has seen popcorn. Here is some popcorn. Now you know what you do. You apply some heat to the popcorn, to the dry, lifeless, dead, inert popcorn. But I would remind you, it is not dead, lifeless, and inert. If this is put in the good earth, and it has the right change in temperature, the right dark and the right light, the right heat and the right cold, the right wet and the right dry, it will sprout and beget itself millions of fold. So it is not lifeless. I ask, when I heat that and the corn pops, why does it pop? Why does it burst so big and beautiful? Answer, there is, however dry it is, there is some water in it, ever so slight a bit. And when that water is heated to the state of steam, it expands 1,700 times. That is, if I have a little droplet of water in there, so big, when I heat it to steam, it is 1,700 times bigger. And I say that's fantastic. One final little inquiry, which you can do yourself. Here is a flask which is filled with colored water and with a one-hole stopper and a glass tube, and you see the level of the water to this place here. Now, you know that if I mechanically squeeze the wall of the flask, the level goes up. If I mechanically squeeze the small edges of the flask, the level goes down. Down, up. Question, supposing I heated the walls of the flask, heated them, would the level go up or would it go down? And so I have left you with a number of exciting and dramatic and stirring inquiries concerning the expansion of stuff. And I thank you for listening.